So again, we're going to describe the motion of a particle located at point P in this 2D plane. However, unlike in the prior examples, P is not allowed to move around freely. Instead, it is constrained due to the fact that it is attached to a rigid rod, which has a length of L. And that rigid rod pivots about a pivot point defined as O here. All right, and so now this particle P is constrained such that it can only move along this circle here, or I should say a better drawn circle with a radius of R, right? It can't leave that path. And so in the prior examples, when P could move around freely, you needed two variables in order to describe the position of that particle. In other words, it had 2 degrees of freedom. However, here, because the P can only move on that circular path, you only need to know one variable. So for example, if you know theta with respect to some reference, so what the angle of this rod is, then you know where point P is in space. And so that's why, for example, I put here, this is a system that has 1 degree of freedom. And again, that's because it's due to this constraint. So constraints can reduce your degrees of freedom. Okay, so now we're going to walk through very much the similar process and essentially try to understand how this constraint affects the position, velocity, and acceleration of particle P. So we start out by first defining a reference frame. We can pick our reference frame wherever we want in this example here. But it makes the most sense to define our reference frame such that the origin of the frame is located right at that pivot point O. And in fact, we're just going to call that, keep calling that O. And we have our 2 perpendicular unit vectors, A1 and A2. And again, we're going to call this frame A. So to define our position vector, which is drawn from the origin here, O, to the point P, essentially along that rigid rod, we have R, O, P. I'm just going to write that this is P, hopefully that's clear. We need to define this vector in the 2 directions of our reference frame, A1 and A2, in the direction of these 2 unit vectors. This is exactly what we did in the last example. So we have here our A1 component of our position vector, and here we have our A2 component. And just like in the prior example, we're going to use a polar coordinate or rotational coordinates, so we know that the magnitude of the vector component in the A1 direction is L cosine theta. And in the A2 direction, it is L sine theta. Okay, so here we now have defined our position vector. Next, we're going to calculate the velocity vector of point P in frame A, which again is the time derivative of the position vector in frame A. And so just to quickly write that out here, we have L cosine of theta A1 plus L sine of theta A2. Okay, so Let's take this time derivative, and as you'll see, it's actually not quite as bad as if um, this particle was allowed to freely move. At least the math or the algebra is a bit simpler. So let's just look at this first term here. In the last example, L, we called it R, but this distance varied with time, and therefore we had to consider its time derivative. However, in this example, L is constant, right? The length of that rigid rod doesn't change, so we can treat this variable as constant. Our reference frame A is again not moving. So the only element that depends on time is this cosine theta, and that's because theta depends on time. So we still have to use the chain rule here, but nevertheless, taking the derivative of this component here is simply negative L theta dot sine theta dot A1. And this is also quite similar if you look at the second element here. So again, this sine theta term is the only one that depends on t because theta depends on t. So we only have to write L theta dot cosine of theta A2. And there you have it. And so that is the velocity vector, much simpler than in the last example, and that's because of the constraint that the rod imposes on velocity. And next we're going to solve for the acceleration. So again, little a of point P in frame A. Acceleration is the time derivative of the velocity vector in frame A. And we are just going to write that out again for completeness. We have negative L theta dot sine theta A1 plus L theta dot cosine theta A2. Again, we're just going to break up the terms just because it's easier to deal with. So we're going to focus on this first term here and taking that time derivative. There's two components here that now depend on time. So this sine of theta and this theta dot. And so we're going to bring back that product rule. I'll just write it out here again, which is that when you have the product of two quantities that depend on time, A and B, that equals the derivative of A times B plus the derivative of B times A. So we'll start out. The first term here is negative L theta double dot. So we're taking the derivative of theta dot. Call that sine theta. And now we're going to take the derivative of this term. Again, using the chain rule, and ultimately what we get is minus L theta dot squared cosine of theta. And that's this A1 term. And now we'll move over to the A2 term here. So again, pretty much the exact same thing. We have two components here that depend on time. So we'll use our product rule. And the derivative of this here is now L theta double dot cosine of theta minus L of theta dot squared sine theta, which is A2. So just to write this out here, because this is our acceleration vector of point P in frame A. Now, just as an aside, if you are uncomfortable with doing some of these, taking some of these derivatives, for example, using the product rule or using the chain rule, just let me know. And if you'd like me to add a video, I've put a video request topic in the discussion forum on Moodle, so you can just let me know and I'll try to make videos to help kind of refresh you on some of these points.